Most discussions about artificial intelligence assume reasoning works in a strict, repetitive loop. The system observes an input, generates a plan, executes an action, and repeats the cycle until it outputs an answer. If that system fails, we prompt it to try again. It might expend more compute, search a few additional paths, and eventually secure a better result. We are observing a static productive state. The system performed more work, but it never altered the mechanical process of how it actually thinks. A system can possess perfect oversight, rejecting unsafe updates, preserving specific invariants, and maintaining meticulous audit logs, while remaining completely intellectually static. Governance alone produces no new cognitive capacity. Repeated inference yields a better immediate output. The energetic paradigm, introduced in a paper by Dr. Wesley Hsu, argues this framing begins too late. The accurate target is recursive intelligence production. Under this paradigm, a completed reasoning cycle actively changes the internal structures that will generate the machine's future reasoning. The relevant unit of analysis shifts away from the single answer produced at time t. The object of consequence is the productive architecture that emerges at t+1, the precise framework determining what the system can represent, search, and reuse on its next attempt. We routinely equate this evolution with adjusting a model's underlying weights. Yet modifying model weights does not inherently improve the physical machinery required to discover, evaluate, and implement future updates. If a machine computes a better answer today, without leaving behind a superior internal architecture for solving problems tomorrow, it is iterating. It has not achieved recursive self-improvement. To engineer this behavior, the system must be formalized as a continuously transforming production architecture. We define this through a specific mathematical vector. This productive state vector consists of the system's representation, its search topology, reusable operators, structural memory, resource allocation, and its validation mechanism. The first mechanical layer of this state is representation restructuring. An artificial intelligence cannot reason over physical reality directly. It traverses an internal mathematical representation of that reality. A poor representation of a problem forces a system to evaluate thousands of semantically similar but useless variations. It makes simple solutions appear combinatorially difficult. Restructuring filters this chaos by distinguishing productive constraints from arbitrary restrictions and separating distinct causes from surface correlates. The system modifies the ontology of the problem. It exposes deep latent constraints that govern multiple surface variables simultaneously. By changing how reality is mapped, the system physically alters which solutions are mathematically reachable. An impossible search converts into a trivial one. Navigating this new mathematical map requires resources. In the energetic paradigm, energy serves as a strict accounting layer for finite computational capacity. This energy is quantifiable. It represents physical GPU time, context budget, experimental runs, and persistent memory bandwidth. Intelligent allocation requires directing this finite energy pool strictly based on marginal structural return. The system learns to abandon paths with low structural yield, immediately redirecting compute toward productive bottlenecks, even if a dead-end branch might have marginally improved the current answer. This allocated energy dictates how the system traverses its search topology. Continuous latent thoughts branch out through this topology. The system preserves multiple high-value alternatives simultaneously, holding them in memory before committing to a discrete single path. Deduction here is a constrained transition policy applied over a structured state space. It relies on mathematical geometry, avoiding the limitations of simple verbal implication. As the system identifies unproductive paths, it recursively modifies its own search graph, physically removing edges to prevent future energy waste. Intelligence compounds because the system learns to permanently rewire the exact pathways it spends energy traversing. The critical mechanism linking representation and search is recursive operator formation. When an AI solves a complex problem using a multi-step trajectory, it doesn't run the sequence again. It abstracts the logic, compressing it into a reusable macro. Applying this operator drastically reduces future search costs. A valid operator must satisfy 4 strict conditions. It must compress reasoning cost and transfer beyond its original instance. It must faithfully preserve the causal structure of the solution, and it must compose cleanly with other operators. By bypassing incremental steps, operators save massive amounts of compute energy, creating a surplus. The system invests that newly created surplus to form meta-operators, dynamic structures designed to improve the operator formation process itself. These new tools require a database. They are housed in the structural memory. Structural memory holds causal failures, boundary conditions, and unresolved contradictions. It requires active management, utilizing deliberate deletion rules to clear out expired facts and false abstractions. Retaining unvalidated operators creates path dependence. False abstractions attract future search, contaminate the logic tree, and waste finite computational energy. Structural memory functions as the physical architecture of the AI's future capacity. It is a record of what changes future reasoning, rather than a transcript of past answers. To prevent this contamination, governance enters the framework under the precise mechanism of controlled inheritance. Governance alone does not create new cognitive operators, it strictly judges them. The inheritance mechanism determines whether a newly produced intelligence update integrates as durable structure, or if it is completely rejected as accumulated structural corruption. The gate checks multiple qualification dimensions: current capability, transfer stability, provenance, resource cost, and total reversibility. This architecture provides a highly falsifiable design, verifiable through a multi-generation experimental matrix. This multi-generational matrix compares a fixed workflow, naive recursion, governed recursion, and the full energetic paradigm. Governed recursion eventually exhausts its search space, hitting a hard performance plateau. By contrast, the full energetic paradigm framework compounds upward, solving harder problems at a stable compute cost. The failure criteria are strict. The thesis is falsified if new operators fail to transfer to hidden tasks, or if performance gains are explained entirely by injecting more raw compute into the experimental runs. The criterion for recursive self-improvement is absolute. A successor system must demonstrate a measured, progressive capability to produce validated future improvements. Safety and governance filter out structural errors and keep a system stable, yet stability is the baseline. Instead, true superintelligence emerges directly from the continuous, recursive restructuring of its representation, energy allocation, operators, and memory.